All right, we're going to look at constraint optimization, and we're going to give an overview of what's expected for the project and explore what's going on with this topic. So I'll first talk about the goals for what we expect when we're done with this, talk about the constraint relationship, and I'm going to talk about an objective function, and then I'm going to go through a detailed example on inbreeding in sheep. Okay, so by the time you're done with this, you should be able to go into a problem, figure out what a constraint is, figure out what the objective function is. You'll be able to discuss the difference between the constraint and objective, and then go through a formal exploration of the relationship between the three variables. Okay. In terms of the project itself, you're asked to accomplish a particular task in terms of finding the best way to do something. But it's also important that you be able to go through and explore the relationship between the variables and figure out if one thing changes, what happens to the rest of the system, and be able to discuss that in a rational way. And then in order to go through and do that, I'm going to talk about a particular example involving sheep. Okay, so in terms of optimization, what do we have? Excuse me. The first thing is we have a constraint, and the second thing is we have an objective. And the constraint is some sort of physical relationship that binds the particular values of the variables that you can look at. So for example, if I'm looking at variables x and y, the only values of x and y that I can consider are those that satisfy some particular relationship. And of all of those, I want to figure out which one's the best. And in terms of best, what do we mean? Well, it depends on what is important to you in a particular context. So oftentimes we'll talk about how much something costs. You may want to minimize the cost, or you want to maximize profit. You may be interested in doing something in the least amount of time. You may want to make something so that the area of the result is as big as possible, or the volume is as big as possible, or as small as possible. Basically, it's anything that you happen to value in a particular moment, right? So the focus is whatever you think is important in this given context, that's the thing you want to either make as big or as small as possible. Okay, so now there's a problem here. Is that discussion in the previous page, we just talked about three different things. We talked about the constraint, which is something that binds two variables together, but the objective brings in some new variable, like the cost or money or time or area, and that's going to depend on the other two variables. So there's three variables going on here, and we've got to figure out how do we talk about those three things together. Okay. All right, so in terms of the constraint, what is the constraint? Constraint is some relationship that tells you a relationship between your two variables. So suppose I have some x and y. The values of x and the values of y that I can consider have to satisfy some relationship. Okay, I can't just pick up any values for x and y. It's only those that satisfy some limitation. So this limitation generally comes from the physics or the basic economic principles or whatever is context you've got here. So for example, you may want to conserve mass. You may want to conserve momentum or energy. That physical principle that you're trying to conserve tells you which values of x and y you can examine. So if these values of y and x give you the graph of those is something like this, then that's a valid point to consider. That's a valid point to consider. But this point out here, that is not a feasible point for me to examine. I can't look at that because it does not satisfy my physical constraints. And the question I'm going to ask is, of all of these points on this line, which one is going to be best? Which one will be optimal in some sense? So what does optimal mean? Well, it depends on the context. So if I'm looking at all these different points and I want to know which one is best, and what is best, it really depends on the context. And oftentimes what happens is, even for the same problem, different people may come up with a different function that defines what is best. So to get at this, you really just got to go through and figure out what do we mean at the time. So kind of a classic problem in this is, suppose we have a rectangle, and we want this rectangle to have some given perimeter, and the cost in this case, or the objective, may be the area. Right? I want this area to be small or large, depending on the situation. And if that's the case, the area is just going to be the height times the width. Right? So that will be my objective, or my cost, in this particular context. And then my constraint is going to be whatever this perimeter is. So I'm going to have an x there and a y there. Or sorry, an x there and an x there, so I've got two x's. I've got a y and a y there, so I've got two y's. And that's going to be some fixed number. Okay? So in this situation, if I'm working with a rectangle of a given perimeter, this is my constraint, and this is going to be my cost. Okay. Now, oftentimes the constraint is the easier of the two things to find. You just apply whatever physical principle that's generally given to you. The objective function, on the other hand, can be very difficult. And so how do you get to that? Because I can't just give you some general thing to look at, or general process. It's really, this is where you have to do your thinking. Right? So the critical thing here is read the question, and when you do that, right, don't just read it once and think you got it. You're going to have to go through and do this a couple times. Don't expect to get this right the first time. The other thing, drawing pictures. And again, it's going to take you a couple tries. That's perfectly fine. That's the way things work. If you don't draw a picture, you should not expect to get these things. These pictures are critical, even if you're drawing what we had before with the rectangle. You can either draw the physical thing, or you can draw graphs of what you think these relationships are. Either way, it's going to be really important to do this, and don't expect to just look at the problem and get it. Right? These can be tough and challenging problems. Then you got to go through and define the variables, what you mean. Right? So if I'm talking about this rectangle, one person may say x and y. You don't know if that's the width or the height, so you got to define that. Somebody else may come along and say, well, I don't like x and y. I'm going to call this the width, and we'll call that the height. Okay? So you need to define this so that you can tell your reader what you're working with and give your reader an idea of what these things mean. Once you do that, then you can try to go through and play games and experiment. What are the relationships that you have? So for example, perimeter and area. And you can write down formulas for these and play with these and try to get a feeling for these, because it may not be immediately clear if the area here, this x times y, is at the constraint or the objective. So go through there and do this, and you may get the wrong thing. You may think that the length of the hypotenuse there, that cross section, may be important. You don't know until you write it down and play with it and try different things. Then you need to go through and figure out what's important. What is the thing that is important in a given context? Is it the area? Is it money? Is it time? Whatever it is. And then finally, make a plan. Figure out how you're going to tackle the problem. Don't just expect you to look at this and know exactly how to do it, because each one of these problems is a little bit different. And if you don't stop and ask, what is my course of action going to be, it's going to be very easy to go off and do the wrong problem. Okay? Once you do that, then you can go and solve the problem. Okay. So let's look at an example. This example comes from this paper. And what did this happen in this paper? This author was interested in how much fleece you can get from a flock of sheep. Right? The idea is, if you're a rancher, you've got all these sheep. You want to get as much fleece as possible so you can make the most amount of money. And in this paper, the author looked at a lot of things. He looked at the number of female sheep. The author looked at how much interbreeding had been occurring. So what's important here is if you have certain sheep that are producing more wool or more fleece, then you want to make sure that those sheep are breeding and will make up the bulk of your flock. Problem is you can go too far. If you go too far, they get too well interbred and they won't produce as much fleece. So you can take these things too far, and the question is what's the balance? And the author here looked at amount of interbreeding and some other factors, and there's very complicated interactions here. What happened? So the author found that if you selectively breed and try to increase the fleece weight, what ends up happening is you increase the number of inbred sheep that you have, and it increases the amount of inbreeding. And so if the amount of inbreeding was too low, you didn't get as much fleece from the sheep that you sheared. But if you went too far, if you increased too much interbreeding, and you got too many of your sheep are inbred, then you could actually go back the other way, right? And you could end up getting a decrease in the amount of fleece that you get when you shear your flock. So the question is what's the balance? Okay, so this is a complicated problem, and it's not an easy one to tackle, and there's some very complicated analysis going on. And also the author did not make the data available. So I'm really here, I just want to try to get to this idea. My agenda is that I want to try to get across this basic idea. So I'm going to just simplify things here and try to make this a much simpler problem and get to the idea, because we're not going to be able to solve the big problem that the author went at before we can solve smaller problems. So let's look at a smaller problem, and then I'll let you build up as we go forward in your life. So I'm going to break this down. So I'm not going to look at male sheep. I'm only going to look at female sheep. The author looked at the level of inbreeding. I'm just going to say they're either inbred or they're not. So the number of sheep that are inbred, I'm going to call this B. I could call that I, but the problem with I is that it looks like a 1 and it means different things to different people and already has some meaning. So I'm just going to call this B. Okay? And then I'm going to look at the ones that are not inbred or non-inbred sheep, and I'm going to call that N. Okay, so I've got two variables B and N. And I want to know what's the relationship between these two things. And I want to know what's the optimal balance that I should try to strike between these two variables. And I've got some total that I have here. I'm going to assume that my ranch can only hold 1,000. And I'm going to try to increase my flock so I get 1,000. So I'm going to assume that I'm not below 1,000 or above 1,000 because I want to try to maximize what I can get. And now the question is what is the balance here? How many inbred sheep do I get for the B, and how many non-inbred sheep do I get for the N? And I want to get the greatest amount of fleece out of this. So in this context, what does best mean? In this case, best means the most fleece, or I want to maximize the number of kilograms of this thing. So I want to maximize the mass of the fleece that I get out of this. Okay. And my constraint is going to come from here, this idea that there's only so many sheep that I can put on the ranch. So I'm going to look at the constraint first and try to figure that out. Right, so the constraint comes from this statement. The total number of sheep is 1,000. And total number, that's secret code for adding up all the sheep that I have. So if I go through and I add up all of my sheep, I should get 1,000. And I've only got two kinds of sheep, the non-inbred sheep and the inbred sheep. So if I add the non-inbred sheep to the inbred sheep, my total is 1,000. And what I have now is, this is my constraint. If I look at this relationship graphically, I'm going to decide to put B on the vertical axis and N on the horizontal axis. That's an arbitrary decision. I just decided to do that. And I'm going to just stay consistent. I could have done it the other way. Doesn't matter. So what do I have? If I take this equation and I solve for N, I get 1,000 minus B. Oops, sorry, I want to solve for B because that's my vertical, sorry. So I get B is 1,000 minus N. This line right here is this line given by that. So if I want to, suppose I want to have 600 non-inbred sheep, that immediately tells me I'm going to have 400 inbred sheep. Right? If I had 600 inbred sheep and 600 non-inbred sheep and 900 inbred sheep, my ranch can't hold that, so that's out. That can't really happen, so I don't want to use that. I can only look at numbers along this line. So all of these values for the number of inbred sheep and number of non-inbred sheep, which one is going to give me the best? And again, by this, I want to get the greatest mass, okay, of the fleece. So of all of these, which one is the best? So now let's talk about the objective. Oh, and I got to be careful here. In terms of the objective, the data is not in the paper, and the author did a whole bunch of different factors. So again, I'm just going to make some stuff up here just to keep this as simple as possible. So let's suppose we did this. Suppose they went through and they did a number of experiments. And in this experiments, remember this is my N, and I'm going to call this the mean, or the mass of the fleece. Suppose they went through and they put together different flocks, and for each flock they had some number of non-inbred sheep. So this was 10 non-inbred sheep, 50 non-inbred sheep, 100, 150, 200, 250 non-inbred sheep. And then at the end of the cycle, they went through and they shared it, and if they had 10 non-inbred sheep, they got 0.031 kilograms of fleece per sheep. And if they had 50 non-inbred sheep, they had 0.4 kilograms of fleece per sheep. And then this was what they got after the whole experiment. And if I graph this, here's what happened. And you can see this general trend is that if I have a small number of non-inbred sheep, as I increase, it's going to increase the amount of fleece I get. But if I'm out here, if I've got a large number of non-inbred sheep, as I increase them, the amount of fleece is going to decrease. So if I were to graph this, it's going to be something like this. And notice, because it's an experiment, it's not perfect. Other things happened. Maybe we had bad weather with this flock and really good weather here, just whatever. I'm going to get some kind of shape like this. And the simplest shape that is going to give me that kind of phenomenon is going to be a parabola or a quadratic. So I'm just going to try to do this with a quadratic and try to keep this as simple as possible. And if you look in the literature and you just go through and do something for a search for quadratic effect, you'll see lots of people try this and do this because of this general shape and phenomenon is common. Okay. All right, so what do we have? For our variables, we have the non-inbred sheep, the inbred sheep, and the mass of the fleece per sheep. And what I'm going to try to do now is I'm going to try to figure out what parabola is going to give me the best fit for this. So what did I do? I went into my favorite search engine, involves ducks, 2 ducks and going somewhere, and I just did a search for Desmos and quadratic regression, and it took me to this page. And then what I did is I entered in the numbers from that previous table. So when I had 10 non-inbred sheep, I had 0.031 kilograms of fleece per sheep, 50 kilograms, I had that. I just went through and I entered all those in, and I typed this equation in. What's important is that tilde, and that's going to tell Desmos to do a regression. And so if I think of this as an squared plus bn plus c, remember, because this x3 is not really x, but it's n, then my estimate for the a is down here is this number. So my best estimate for a is the 0.000329 blah blah blah. My best estimate for b is 0.008789 blah blah blah. And my estimate for c is about minus 0.0117 blah blah blah. Okay? So that gives me what this parabola is. And what did we have? This is my mean fleece, or the mass of the fleece per sheep, and this is the number of non-inbred sheep. And if I want to maximize my mean fleece, my mass of the fleece, basically that's it up here at the top of the parabola. I can do better than that. Oops. So whatever that number is, that's going to be the number of non-inbred sheep that I want. That's going to make this as large as possible, because that's going to be where I get to the very top of that parabola. So what do we have? So I took these numbers, came from the experiment. I figured out the best parabola that would fit those things. I got this, and I got this for the parabola. Now I got to be careful here, right? I've got, for these numbers, I've got two significant digits. So this is, don't do this, right? This is bad. So this should just be negative 0.000033. Let me clean that up. This should be 0.0089. That should be negative 0.012. Right? If you work with these kind of numbers, it just doesn't make any sense, because right, out here there's no meaning to what those mean, because you only have this much assurance about what these numbers actually mean. And so if you insist on using a number like this, I will find your chemistry professor, and we're all going to sit down and have a little talk. Okay? So be careful. All that stuff you do in chemistry is important and it matters. All right, so let's go back. Let's recap what we have now. We have a constraint. We can't have more than 1,000 sheep. So there's my constraint. I got into my data and I found out that the mass of the fleece, that should be MF, sorry, is my best approximation is given by this thing right here. And this is my objective that I want to maximize. So I can just do this. I can just go get a formula in the book, blindly plug this in, I get some number. Once I get in, I can come back to my constraint, use this to calculate B, and I'm done. No. That's really not what happens, right? What happens in practice is we aren't right at that perfect magic number, right? Things change. As we go from year to year, the flock is going to change. I'm going to try different things and see what happens. So I don't want to know what's the exact perfect thing. I want to know what's going to happen if I change certain things. Will it get better? Will it get worse? And if so, by how much or how little? Okay, so the things are always changing. We want to know what happens when we make some kind of change. And we also want to know what's possible. Right? What can I expect to get out of this? I want to know, what's the highest I can expect, what's the lowest I can expect, and that's going to help me make plans in terms of what's going to be going on next year and how much I can expect to take to the bank, how much I need to save, and how much I need to have in the bank. And I also want to be careful. These are approximations, right? If my estimations are off by a little bit, suppose I have 1,001 sheep, suppose that those estimate for those coefficients were off by a bit, what's going to happen? This is the key thing. We're not here to just get a number. We want to understand what to expect out of this, right? We want to know what's going on with the patterns, what are the range of things that can happen. If I tweak things a little bit, how are my results going to change? and I want to understand what's going on. Okay? So just getting some n and some b at the end is not really helpful. Okay, so let's go back. What do we have? We have our constraint. We have the mass of the fleece mass. Now, there's a problem here, right? I've got n, I've got b, and I've got this, and I've got two equations. How do I make sense out of three variables when I've got two equations? And let's look at this graphically. So this is my n plus b equals 1,000. This is my fleece mass is, whatever number I had times n squared plus whatever times n plus whatever I had there. Right, that's that parabola. Notice on the horizontal axes, that's n and that's n. That's fine. Those are the same, so I can compare those. That's the number of inbred sheep, though. That's b, right? This is number of sheep here on the left. On the right, what is this? This is the fleece mass, right? This is how much fleece I'm getting here. This is kilograms. So there's no way I can just superimpose this and try to make any sense, right? I've got these three variables here, and I need to somehow bring them together. And so here's the game I'm going to play. I'm going to say, suppose I pick a value for my fleece mass. Suppose I say, what if the value of the fleece mass is 0.32 kilograms per sheep? I'm going to ask, if I get that, right, then what's that mean in terms of my number of inbred sheep and my number of non-inbred sheep? Okay, so what do these two numbers mean, and how do I think about it? So if I do that, I need to try to take my equation for the fleece mass and bring it in terms of both n and b. So how am I going to do that? Now there's a lot of ways to do this. This is just one way. You can find other things that people try. Just pick one way and go with it and be consistent. What do we know that if the number of inbred sheep gets really big, or I'm sorry, if number of inbred sheep is small, this is the number of non-inbred sheep, right? So if this is big, we should expect the fleece mass to get big. Likewise, if the number of inbred sheep is, I gotta be careful, this is non-inbred sheep, sorry. If the number of inbred sheep is getting bigger, eventually we expect our fleece mass to decrease. Okay, so if this is already big and gets bigger, right, this thing is going to go down like that. Okay, so here's what I'm going to do is I'm going to write this as L times n minus b. And I'm going to put this minus b here, this m minus b here, because I know this is going to get smaller as b gets bigger. And I don't know what m is. And I know that as this n gets bigger, this is going to get bigger. And I'm going to have to shift this up some amount. I don't know how much yet. So the question is what's the L, the m, and the n? All right. Now you probably look at this and thinking, what the heck? Why do I know this even works or makes sense? Well, first of all, it's going to just get to this idea that these two interactions are going to play off one another and work against each other. So just taking two numbers and multiply them is the simplest way to get an interaction. So this is oftentimes people just try this, see what happens. If it works, it's great. If it doesn't work, we try something else. In this particular case, I know it's going to work. Because if I take my constraint and solve for b, I get this equation. So this says that if you give me the number of non-inbred sheep, I can figure out the number of inbred sheep through this. If I take this and I plug it into the formula for b from the page before, I now get this equation. And because this is a linear equation, what happens? If I multiply this through, I get ln squared plus what? M minus 1,000 times L times N, and then plus capital N. By the way, mathematicians are case sensitive, so capital N is different than small n. So this is just a standard parabola here, and I've got two parabolas. I already know the fleece mass is given by this. So in order for two parabolas to be the same, I just have to make the coefficients the same. So I can immediately look at this and say, okay, n is minus 0.012, L is this, and then I have to set this whole thing equal to this and then solve for the m. Okay, so I'm not going to go through and do that because it's not polite to do algebra in front of people, right? And we want to keep this safe for kids. So I went through and I did that, and I found these values for L and M and N. Okay, so that means now I'm just going to use this for my approximation. This is really should be an approximation, but we're going to be a little sloppy here. My three variables are now wrapped up into this one equation. My fleece mass is here, my N is here, and I'm going to solve this thing for B. Okay, again, I'm not going to do the algebra here because that's not polite. I get this equation. Let me rewrite this. What does this mean? So now I'm going to just suppose that my fleece mass is a fixed number. I'm just going to set this to some particular number. So what I have, like 0.32. Suppose it's 0.32, and I'm going to ask what happens here. What do I have? This is my parent function, is 1 over n. Let me change colors here. So it looks like that. What's going on? This right here is going to be a vertical scale. So this is going to, if I make Fm smaller, n minus Fn gets bigger, and this is going to stretch this out vertically. If I make Fm bigger, n minus Fm gets smaller, and it's going to squeeze it in vertically. And this is going to be a, vertical shift. So that's just going to shift it up some amount. Okay. But what's important here now is this equation has a b here from my constraint. I know this. My vertical axis on my constraint plot was v, and with this relationship now, this is what I'm going to be on the vertical axis. So now I can relate this equation and this equation as long as this Fm is some fixed number, right? If I fix that as some number, I can now compare these two things, and I can ask, what happens if I make Fm a little bigger or a little smaller? What's going to happen to this function? So let's look at what happens. So here's my constraint. So B, be careful here. B was what? 1,000 minus n. I get this straight line. I can only consider points on this line. Of all these points, which one is going to make Fm as big as possible? Okay. So I'm just going to say, suppose Fm is 0.12. Just an arbitrary number. I just picked it and asked what's happening. For this, let's see. There's only two possible values for n. So this is my non-inbred sheep here. This is my number of inbred sheep here. So this thing here is around what, 250 and what, 750 or so. So that's one possible way that I could have gotten a mass of 0.12 kilograms per sheep. The other way is up here, so this is going to be around 5950 or so. Right? If I was there, then I could get the same amount of fleece per sheep. So there's two ways I could do this if you tell me you want to get 0.12. Suppose I want to do better. Okay, suppose I want to get 0.22 kilograms of fleece from each sheep. What's going to happen there? Notice this basically stretches this up a little bit, and now where these intersect is right here and here, and it only changed a little bit. So this is saying that if I do a small change in my N and B, right, I can get almost double the amount of fleece out of this. Okay. What happens if I want 0.32? Again, now there's two places where this can happen. Again, this is a small change. So this small change is going to give me another 50% change. So now notice this is about the same amount of change as I went from 0.12 to 0.22 to 0.33 or 0.32. That initial, when I was out here, that small change almost doubled the amount of fleece I can get, but now that same amount of change only gives me a 50% increase. So I'm not getting as quite a big a payoff now as I got before. So now going to make a big change, I'm going to have to make a bigger difference here. So let's try 0.52. Let's get greedy and ask, what happens if I want to get 0.52 kilograms of fleece per sheep? And now I'm going to have to make a big change to get that amount of fleece, right? So I'm going to have to shift way up to here in terms of what I get for my, oops, this is N and B. And notice it does intersect at these two places. So there's still two places where I could get that amount of fleece from the sheep. So let's get really greedy and try to get 0.72, see what happens. Now note, this does not intersect my constraint. There's no possible way for me to satisfy my constraint and also get 0.72 kilograms of fleece per each sheep. Right, so if my business partner goes and promises somebody that they're going to get this much fleece out of this flock, I know that we're in trouble. Right? I know it's time to skip town because it's going to hit the fan. Right? So the optimal amount of fleece is going to be somewhere between here and here in terms of what I need for my N and B. So the question is what value can I set for my fleece mass and still touch this curve? And so it's going to be somewhere between 0.72 and 0.52. And the question is can you play with this and get this figured out? More importantly, can you talk about what happens when you change the fleece mass? What happens to these points in order to achieve that objective? Okay. Now there's a problem here with how we have things set up, and I kind of try to ignore that and gloss over it, but it's important to talk a little bit about part of the problem here. What did we have? We had that our B was M plus N minus Fm over L times 1 over N. In this case, N is negative and L is negative. And so this this term right here is going to be negative over negative is positive. And as you increase Fm, you're making the whole thing bigger. And so you're going to be pushing these solutions up. You're basically stretching them up. Because of this, what you're always going to be doing is after you stretch this, you're going to be taking your solution and shifting it up some M. So what was our axes here are N and B. And so you're always going to have this getting really close to M but can't go below it. And what this is saying back in our original graph here, right, we can never really get below this. And there's no way for us to get solutions that are going to occur down in this part of the curve. And that's indicating that there's probably an issue with how we have this thing set up. Either there's a problem with our objective function, or there was a problem with the data. In this case, it happened to be the data. The data that I happened to make up was kind of, because it was artificial, gave us some weird results here. And it was really bad data because our objective function is such that we can never really examine what's going to happen when we have the number of inbred sheep get very large. And that's just not physical and doesn't help give us insight into what's going on here. So what happens is that these kind of things happen, and it's very important to go back and ask, do the results make sense? Do these patterns give us the information we're wanting, and is everything consistent? In this case, it's not. And what you end up happening is we get lots of discussions about what should be the form for objective function. Is there a problem with the data or our observations? It could be a lot of different things, and it leads to all kinds of interesting discussions. Sometimes you end up at the bar, at least you used to, but now you end up on Zoom drinking alone. But it's very important to go back and ask, what does this mean, and are these results consistent with what we expect, and does it give us the insights we're hoping to find? Thank you.